Yeah, that's true. That is true. We're going to do a last quiz Friday, a week from today. No. Um, so one more quiz. Right. So you can prepare for it mentally right now while I lecture. So Friday, the 10th. Yeah. So it's the last thing we're going to do in this whole class is take a quiz. 5:10. And I'm going to try to make it sort of easy-ish so that everybody gets points and feels good about it. I mean, come on. What is one of the questions going to be on it? Yeah, exactly. Well, now it's probably not, but no, but that's so important. Those need to be in your head. And when somebody asks you, like, what did you guys cover in deform? That's what you should say. Like, we learned what the restrictions are on the materials we can cover. Ooh, that's a good one. How many variables? 2. Yeah, only Young's modulus and Poisson's ratio. Yep, and then you use that for all of the 36 entries. Yeah, but they're all just based on those 2. You're right about that. I mean, they're right. There are 9, 10, 11. There are 12 non-zero elements, but they're all determined by Young's modulus and Poisson's ratio. Yeah. Ellie, do you have a question? For shear force, we can only do it for rectangular and circular, and we can only do circular along the neutral axis. No. Right. No, it doesn't. But that's fine. If you put those other 2. Mm-hmm. Yeah. Okay. Shut up now. Time to be serious. So one important equation in mechanics type engineering, one important mechanics equation, I guess I'll say, is the differential equation, let's call it y double prime plus some constant times y is equal to 0. Okay, that's that is a second order ordinary differential equation, and you're trying to solve so you want to find a functional representation, a function for y. You want it over all the values of the independent variables. Can anybody off the top of their head come up with an application of an equation like this? Anybody? Yes, exactly. So just this morning in dynamics, we covered this. Okay, we saw that if you have a mass spring system, that gives you the equation x second time derivative plus k over m times x is equal to 0. What? Just system. I mean, just so if this has a mass of m and this has a spring constant k, and there's two ways to solve this system. So this is sort of an aside, you know, for example. But there are two forms to the solution to the equation so I'm writing it as y double prime plus c times y is equal to 0. The first way you can write it, and these are equivalent to each other, you know, is the one that we used in dynamics this morning. We haven't done much with it. We haven't done anything with it yet, but we had the form that y as a function of x, well, really for us it was x as a function of t, but is equal to some constant times the sine of the square root of c times x plus k, well, no, don't call it that, plus, let's call it plus b. And a and b are constants, and you figure those out based on the boundary conditions. So that's one way you can write it. And the second way you can write it is that y of x is equal to a times the cosine of square root of c times x plus b times the sine of square root of c times x. And those a's and b's aren't the same thing, but either of those is a valid general form of the solution. Which one you choose just depends on sort of how you want to think about the problem. But really, all you're doing in either case is both of these are sinusoidal functions, okay? And adding cosine and sine together with different coefficients just has the effect of shifting the sinusoidal shape horizontally. And that's the same thing that having this phase shift angle in there does, okay? So these do the same thing. Obviously, I mean, they're solutions to the same equation. Okay, in dynamics, we use this one. For the spring mass. And this is the form that we're going to use in deform for column buckling. So that's what we're getting into now. And one thing to get ready for, notice as we go, is when we do this in dynamics, like almost everything in dynamics, our independent variable is time. And so we're coming up with a function of time, you know. And so what we have is x of t is equal to a sine of square root of something times t plus this, okay? Well, in deform, we don't do anything that's a function of time. I mean, we haven't. So we're going to be solving this function with an independent variable that represents a spatial dimension, you know. So this function is going to represent a shape, not how things change in time. Okay. All right. So column buckling. The last topic.
So we bring questions on Monday.
Yeah, I mean, I'm not going to finish this today, but yes, we'll have all the time for questions that you could imagine. And then I have some other little topics that, later on you might like to have heard about or something, but we're not going to do any problems on them or anything. Um, okay, so the idea is that for long, slender shapes, um, and actually in compression, um, failure occurs in buckling at lower loads than it occurs in pure compression. So if you have the first example we're going to look at is a thing that we're going to treat as being pinned at the ground and then pinned up at the top. You can think of this as two pin joints. And these are rollers. Move this down a little. And so if you apply a compressive load P here, okay. What? Yeah. Was was that like angry sarcasm? um, so we could calculate the load, like if you knew the amount of stress and strain that would cause this to just smush into failure, we could calculate that based on this material. And that would take a relatively high load P. But before you get to the load P that would just smash it, you would get this effect where it bows out to the side, and that's an exaggerated picture. Although I guess actually the idea is that by the time this has happened, we've already gone way past the buckling point, but there's a buckling point where when you get to a high enough force P, this thing isn't strong enough to fight its way back straight when it gets bowed out. And so eventually it gets to a point where this force makes it bow out to one side or the other, and it's not strong enough to get back to vertical, and it smushes in half like that, sort of folds in half um, rather than just going straight down. Yes. A spring? Yeah. Mm-hmm. I mean, uh, there are things you can do, and we'll talk about some of those things. But this is just an important feature to keep in mind. It's a concern to have when you're dealing with long, slender members. Notice that so this is um, so the type of joints that you model it as has a big effect on what that buckling load is. If they were fixed, it just depends how strongly they were fixed, I guess. But if they, yeah, you can have different, well, yeah, like if this was fixed, then for example, and this is all the kind of stuff we're going to talk about, just like we had beam requirements when we talked about deflection that had to do with a fixed joint, we would have this requirement that says, okay, here, right at the floor, it would still have to be vertical, and that would affect its ability to buckle, and so that buckling load would go up. So, so notice though that for this to happen, it happens, it's more likely to happen. It will only be a problem when you have long, slender members. If you have a member that's, this tall and this wide, it's impossible to make that thing buckle to the side. And so the length and the cross-sectional area is going to be an important part of this. Yeah. We are, I guess, the area and the length are going to be built into the formula. And so if you have a really short, stumpy object, you would just get a buckling load that was higher than the compressive failure load, and so it'll just come out in the math that we have. Okay, so how are we going to calculate? What we want to calculate is when do long, slender shapes in compression become unable to straighten back out? And that's really what the idea of buckling is about. Unable to straighten back out. You can also think of that as when do they become unstable. So a stable system is one where you introduce a little perturbation to it. There's some imperfection or something that makes it pop out to the left a little bit or whatever, a tiny little bit. A stable system has the strength to go back into a vertical shape. When that little perturbation happens to the side and it's not strong enough and the weight just makes that continue to bow out, then that's an unstable system, and that's when buckling happens. Okay, so let's think about this shape here. So here's figure 1. So think about a deformed beam from figure 1. Which side is it going to? And let's think about the loads that are acting on it. So it's shaped like this, and if we isolate the whole thing, the length of this is L. I mean, that's the undeformed length, but we're assuming small deformation, so the undeformed is equal to the deformed. And we have two forces acting, P here to counteract this P. Okay. And then let's draw a free body diagram of the lower half. and it looks like this. So there's the P down there. The total length this way is L over 2. We'll call this distance the deflection V. Yep. The what? Oh, it doesn't matter. It's slender, and yeah, we don't care about that. But we're doing small deformation, so it's not shaped like that. It's like when we look at what we're considering, it's still basically straight. You know, that's just an exaggerated picture. And so what, basically now this is an internal loads calculation. And if at the point where this becomes unstable, okay, if you deform it like this, so if it's stable and you deform it like this, it's not going to be in equilibrium, right? Because what's it going to do? If you bend it like this and it's stable and let go of it, what's it going to do? Spring back, yeah. So as long as it's stable, it can't be in equilibrium in this position. Okay. At that exact moment when it becomes unstable, there's an exact balance between the forces here and the ability of that moment to the bending moment to straighten that back out. Okay, they're fighting to a draw. You know, that's the boundary between stable and unstable. So let's assume that this is an equilibrium because that's the point we want to look at. And now let's figure out the internal loads here that put this in equilibrium with this required external load. Okay, well, we know there has to be an equal and opposite force P. Now, this is a couple that, you know, would tend to rotate this thing, okay? So there needs to be another couple to counteract that. Well, it could come from the shear force, and really you could just do this as a sort of a funky internal loads problem. We usually do it with straight beams, but you could do it with a shaped beam like this. But the shear force still has to be 0 because there's no, you could produce a moment that does what we need up here, but then there'd have to be a horizontal force that way, and there isn't. So the only other way to do it is a bending moment up there. And so if the force P up at the top is trying to make this rotate clockwise, there has to be a couple over here, M. It's going to make it rotate counterclockwise to counteract it. And we're going to assume equilibrium because that's the instant when the system becomes unstable. And let's use, yes. No, there wouldn't be any, so torsion would be like twisting this way, you know? So no, the only thing that there has to be is in the Z direction, the way we think of it. That's the bending moment. And so now, we are going to, so if you go to rotational Newton's second law, okay, and this is the about point. what you get is the bending moment M, and then minus the force times the deflection is equal to 0. And actually, if our coordinate system is like this, like it always is for beams, no. Our coordinate system is like this, right? Then V is actually, so I sort of drew this to the wrong side is what I'm saying. This would actually be a negative V. It would make more sense if I just drew it the other direction. And that, because that's a negative, you get the double negative there and it's positive. So see, the problem is that I drew my deflection going in the negative y direction. Is it worth scribbling this out and doing it again? Probably, isn't it? Yeah. All right, scribble that out. Scribble this out. I guess scribble this guy out. I don't know. Do I look like Bill Gates? I guess. Okay, so now we're talking about this. And the lower half free body diagram. We have a coordinate system like this. This distance is L over 2. And this is V. And the forces are a P this way, a P this way, and a bending moment M. Yes? Would be what? On the bottom? This is, at the bottom is a pin joint, so that can't provide any moment. That can't provide any couple. The pin joint can only provide forces. And so this M here is the internal bending moment applied by the fixed joint with the rest of the material. And so rotational Newton's second law says the couple plus the force times the deflection is equal to 0. Okay, so now we have two variables in that equation. How are we going to express this in terms of a single variable? And where the derivatives come in is we're going to go back to that idea of Euler-Bernoulli beams that we used for calculating the deflection. So remember, the deflection is related to the bending moment by m over EI of the material is equal to the curvature and the curvature is a mess unless you can assume small deformations, which we always can. So kappa is simple for small deformations. Really what it is small absolute values of deflection prime. Then the curvature is, just, we can treat it as equal to deflection double prime. Yeah. Yeah, so the confusion was the way I did it before. I drew it with a negative deflection, and so it was sort of confusing to get an idea of, to try to get an idea of the direction of the rotation the moment was applying. So here I have it drawn with a positive deflection, and it's easier to get your signs right. Is that why the rotation? Yes, that's right, because you can see that this moment is going to make it rotate counterclockwise around that base point. Before it looked like it was making it rotate clockwise, but that was just because we had a negative V, and it's sort of hard to show that. Okay, so if kappa is equal to the deflection double prime, then the fact that the curvature is equal to m over EI says that the bending moment is equal to EI deflection double prime. And so plug that into rotational Newton's second law. And you get EI V double prime plus PV is equal to 0. And divide everything by EI, and you get that V double prime plus P over EI times V is equal to 0. And that's the second order ordinary differential equation of the form that we just did this morning in dynamics. And okay, so the solution to this, I'll call this star. The general solution to equation star V as a function of x is equal to A times the cosine of the quantity square root of P over EI times x plus B times the sine of the quantity square root of P over EI times x. And we have two constants we need to figure out. So let's see, we're trying to figure out the value of okay. So we need two boundary conditions. To solve for these constants a and b. And the two we're going to use are first, at x equals 0, at the pin, the deflection has to be 0 because the pin's locking it in place. So at x equals 0, v is equal to 0. And then the second one we're going to use is at x equals L, deflection's equal to 0. The actual top, yeah. So where's this picture? So this is L. And so because of the rollers, because it's locked in place up here horizontally, the deflection has to be 0 here. Over here, the deflection isn't 0. This is the biggest deflection. You know, I mean, we could do something with the deflection prime or something, but this is the easiest way, is just to say deflection is 0 here and deflection is 0 here. Okay, so first, at x equals 0, we need v of 0 to be equal to 0. And our v is this form, so we have a cosine of, if x is equal to 0, all that stuff is 0. Plus b times sine of 0 is equal to 0. This one goes away because sine of 0 is 0. So we don't know anything about b. But cosine of 0 is 1. So we have a times 1 is equal to 0. And so a is equal to 0. Okay. So we're going to update our general solution. And now we have that the deflection as a function of x is equal to a times cosine. Oh no, a is equal to 0. So it's equal to, you know, that first term goes away, and all we have is b times the sine of the quantity square root of p over ei times x. And now we'll go to the second requirement. So at x equals L, we're requiring that the deflection at L is equal to 0. And so that says that b times the sine of the square root of p over ei times L, we're doing it for x equals L, is equal to 0. And we thought, I mean, probably, that we were trying to find a value for B, but it turns out that the value of B doesn't have any effect on when this goes to 0. What matters is that the stuff inside here is either equal to 0 or pi, or multiples of that. So you can think of this as requiring that the square root of P over EI times L is equal to N pi where N equals 0, 1, 2, so on. And so if you rearrange this, remember what we're trying to find is the value P where this thing becomes unstable. So move stuff around a little bit, you get square root of P is equal to square root of EI times N times pi divided by L for N equals 0, 1, 2. And then take the square of both sides, and P is equal to EI times N squared pi squared over L squared for N equals 0, 1, 2, and so on. Well, there's one last thing to do, and that is notice that when N is equal to 0, we get the trivial solution, no load, no deformation, and so we'll get rid of this one. And that says that the final answer is the minimum buckling load and we're going to call that the critical value of that load P, is the smallest value of P you can get here, so that's just using N equals 1, and you get P critical is equal to E times I times pi squared over L squared. This corresponds to an N equals 1. Whew. That's a formula for a beam that's buckling that has joints like shown, that's buckling in the mode where it just bulges out at the center. Okay, but now what we're going to do is use this idea to talk about, well, what happens if it's not allowed to, if the deflection is restricted at the middle, or what happens if we change the joint types at the end? How does that change our calculation of the critical p-value? And basically, we want to just see how restrictions that we put on these beams can keep us from failing in buckling at such a low value. Let's look at this for a second, too. I mean, I think it's sort of intuitive how this formula works. So what we want What do we want? P critical high or P critical low? We want it high because this critical value is where it collapses. Okay, so first of all, P critical gets higher if you get a stiffer material or a cross-sectional shape that's more resistant to bending. Okay, so those both make sense. If your material is hard to bend, then it's going to be a higher critical load. And the longer the thing is, you get, and that's squared, so that's really important. Like, as you make this thing longer, you're having a drastic effect on the critical load that buckles it. Yes. No, the shape is all contained in that eye. So that's area moment of inertia. Yep. Mm-hmm. Yeah, the two eyes that we've dealt with are area moment of inertia and the polar moment of inertia. And polar is torsion, so this is area. So we want a high P critical. And P critical comes from a high Young's modulus, a high area moment of inertia, or a low length. Okay, so that's all for today, and then we'll just talk about some of these other conditions. It's just going to change the form of the differential equation a little, change the form of the boundary conditions a little, and we'll see the effect it has. Okay, that's all.